What if the most spectacular collisions in the universe aren't just rare, but impossible? Beyond a certain distance? You've probably heard that galaxies can merge, like cosmic whirlpools gradually swallowing their neighbors. But there's a twist. When two galaxies are pushed far apart by the expansion of space, they can stop getting closer, even though gravity is still trying. The surprising question is, where exactly does that break happen? And why does it look like galaxies reach a ceiling just beyond light speed? It sounds like a contradiction. After all, nothing can travel faster than light.
Yet the universe behaves as if mergers stall at the light-speed horizon. Today, we'll unpack that horizon using dark energy, and we'll see how it reshapes the cosmic stage so thoroughly that two galaxies can drift apart forever, even when their mutual gravity would be strong enough in a static universe. This matters because it determines how structure forms and how we interpret the faint ancient light that tells us what's going on out there, beyond our view. Before dark energy, the story of cosmic growth was simpler. After the Big Bang, the universe was dense and hot, then cooled and expanded. In that early era, gravity won. Small density variations grew into filaments and halos, eventually birthing galaxies and galaxy clusters. Astronomers watched the large-scale distribution of galaxies and found it consistent with an expanding universe where matter clumps over time. But then, in the late 1990s, observations of distant supernovae revealed that the expansion isn't just continuing, it's accelerating. The simplest interpretation introduced a mysterious component with negative pressure: dark energy. In the standard model, dark energy doesn't pull things together like matter does. Instead, it drives an ever stronger repulsion on the largest scales, making the universe's expansion behave differently depending on distance and time. In the before picture, you might expect gravity to win everywhere given enough time. But once acceleration enters the game, that expectation quietly fails, and the failure has a location, a horizon in which the cosmic expansion outpaces the ability of gravity to bind two galaxies. Here's the core mechanism. Imagine space itself as an expanding fabric, like dots on a stretched balloon. In an ordinary Euclidean sense, light speed limits how fast information moves through space, not how fast space stretches between distant regions. Now add gravity. Galaxies attract, so they want to move together relative to this expanding fabric. But dark energy changes the rules of the background expansion. A useful way to picture it is through a contest: gravitational attraction versus the stretching pressure from an accelerated expansion. For two galaxies at distance d, the effective pull trying to reduce d scales roughly like mass and inverse square of distance, while the push from dark energy grows in importance with distance. Past some scale, the repulsion dominates the dynamics. There, the galaxies are not merely moving apart because they were flung outward, they are dynamically prevented from ever re-entering the gravitationally bound regime. The horizon arises from a relativistic bookkeeping of expansion. Even though no object locally outruns light, the recession velocity between far separated galaxies can exceed light speed because it's not a motion through space, but an expansion of the metric itself. The key is that the ability of one galaxy to influence another depends on whether gravitationally bound motions can overcome the cosmological expansion. Dark energy effectively creates a boundary. Beyond it, the worldlines of galaxies separate so that their gravitational influence cannot gather the separation into a merger. Think of two dancers on opposite ends of a treadmill that's speeding up. They can pull toward each other using a rope, but if the treadmill's belt expands their separation faster than the rope can reel it in, the dancers never meet. In the universe, the belt speeding up is dark energy's accelerated expansion. Astronomers and theorists formalize this with a notion closely connected to the Hubble radius and the static radius, a scale where the outward effect of expansion balances inward gravity. The exact value evolves with time because dark energy's influence changes as the universe expands. In a simple model with a cosmological constant, the radius grows or shrinks depending on the cosmic parameters, but the essential message holds.
there is a maximum region around a galaxy where the galaxy can remain gravitationally bound against the accelerating expansion. Outside that region, even if two galaxies are currently near enough to notice each other, the expansion wins, stretching the connection into insignificance. That's why merger rates peak at certain epochs and then decline for very distant partners, creating what looks like a dark energy horizon in the cosmic web. So, what are the broader implications? First, it tells us which structures can assemble. Galaxy mergers are a major engine of galaxy evolution. They trigger starbursts, reshape morphologies, and contribute to the growth of supermassive black holes. If dark energy suppresses the inflow of matter in satellite galaxies beyond a distance, then the universe's future merger activity slows down. Second, it affects how we interpret observations of large-scale structure. We see galaxies clustering on scales that reflect the interplay between gravity and expansion history. As dark energy strengthens its dominance, the growth of structure saturates. New clumps become rarer because the supply of nearby partners dries up. Third, it reframes the meaning of causal separation. The horizon is not a wall you hit with a spaceship. It's a limit on what can ever communicate or collapse into the same bound system. That becomes crucial for cosmology because the cosmic microwave background and distance surveys encode information from regions that were once in causal contact, but not all regions remain so. Finally, the idea challenges intuition. The stalling beyond light speed is less about faster than light travel and more about how space-time geometry changes. Dark energy doesn't violate relativity. It exploits the fact that relativity permits expansion rates to outgrow light speed without local causality breaking. To close the loop, let's stitch the story together. Galaxy mergers depend on gravity-binding matter into a common gravitational system. Dark energy, behaving like a smooth component with negative pressure, drives accelerated expansion that grows in influence with distance. That creates a dynamic boundary, a horizon, where the outward expansion effect overwhelms the inward pull of gravity. Beyond that boundary, galaxies may still be around in our sky, but the universe's geometry prevents them from approaching closely enough to merge. So the phrase beyond light speed is a hint at an illusion. Recession velocities can surpass light speed due to space expanding. Yet the real stopper is whether gravitational binding can ever overcome that expansion. In other words, the horizon is a merger limit, not a speed limit. When you think about the universe this way, it stops being a stage where gravity fights expansion everywhere. It becomes a map with regions that will inevitably never coalesce. If you want more cosmic mechanics, subscribe for the next deep dive into the universe's hidden rules.